In this video, we're going to finish up example 8 in section 3.8 and look at part B. So recall, for example 8, what we want to do is determine the convergence or divergence of the given series by using that limit comparison test. So to summarize, we're given a series of b to the n's. We want to know, or we want to find a series a to the n to compare it to. And by comparison, we're going to look at the limit of the ratios of the two terms. Okay, so let's go ahead and get started. So first, I just want to look at the terms in the series that we're given. And we're going to do just some scratch work. Play around with the series a little bit, get familiar with it, find that a to the n series to compare with. Okay, so our terms, our b to the n terms, look like the following. So they look like 3 to the n over 2 to the n squared plus 4n plus 1. Okay, so we need to find an a to the n series to compare. So we need to find those a to the n terms. Okay, so how do we find the a to the n terms? Well, here's the strategy. We look at the b to the n's that we were given, and we're going to determine the dominant or kind of the loudest term in each of the numerators and denominators. Okay, so the numerator, the largest term is that n. So 3 is just a scalar. It's not too much to worry about, but n is that dominating term. So n will go in the numerator of our test series. And in the denominator, the loudest or biggest term is that n squared. So in our denominator, we're going to use n squared. So when we're thinking about the an series to use, it's kind of similar when we're computing a limit, where we kind of want to know what's the dominating term in each of the expressions. And you're going to see more examples. You're going to get more practice of choosing that a to the n, so it will start to feel more comfortable. Okay, so we have the a to the n terms, could look like n over n squared, but that's just 1 over n. Okay, so in order to use this series using an terms, we need to know whether or not this series converges. So let's make a note about whether or not it does. So our a to the n, that's equal to the series of 1 over n. And notice this is a p series where p is equal to 1. So we can write that down. This is a p series with p equal to 1. So go back in your notes and determine if this series converges or diverges. You can go ahead and pause the video to do that. All right, well, if you look back, if p is equal to 1, that series diverges. So that means if we're able to find the limit of the ratios of the terms, and that ratio or that limiting ratio is finite and positive, that means our starting series will diverge, since our a to the n series does. So now we need to set up that ratio. So now we need to consider, and maybe I'll just make a note of that so it's clear kind of what our next step is. So find a to the n is our first step. Now we need to compute limit of ratios of the two terms. Okay, so we need to compute the limit as n goes to infinity of b to the n over a to the n. And when we compute this limit, it's going to become clear why we chose the a to the n we did, using that method of considering the dominant term in the numerator and denominator. So this limit is equal to the limit as n goes to infinity. So I'm just going to plug in my b to the n and a to the n. So b to the n is 3n over 2n squared plus 4n plus 1. So then I'm going to multiply by the reciprocal of this 1 over n. So I'm just saving a step here rather than writing the whole division of the fractions and then multiplying by the reciprocal. I'm just doing it in one step here. So then the reciprocal of the a to the n would be n over 1. And now I'm going to multiply. All right, I'm going to drop down here to the next line just so I give myself enough room. So now we're looking at the limit as n goes to infinity of, so I'm going to multiply numerators. So that's 3n squared over, and then I just multiply by 1 in the denominator, so I'm left with 2 to the n squared plus 4n plus 1. So what's going on with this limit? Well, as n goes to infinity, both the numerator and denominator go to infinity. So using L'Hopital's rule, we have that this becomes the limit as n goes to infinity of the derivative of 3n squared is just 6n using the power rule. Derivative of that denominator, well, we just have a polynomial. So we're using power rules here. The 2 comes down, plus 4. Okay, so what's going on here? Well, this is simplified a little bit, but we still get infinity over infinity. So we just use L'Hopital's rule again to determine that this is equal to the limit as n goes to infinity of the fraction of derivatives. So the numerator now is just 6 and the denominator is 4. This is just a fixed number. So this limit is just equal to 6 over 4, which reduces for us as 3 over 2. Awesome. So what this means, so to kind of summarize then, using the limit comparison test, that means that our Bn diverges. Since this 3 over 2 is positive and finite. Okay, so we have all the scratch work laid out for us. So now we just need to write this up into a formal proof. All right, so let's go ahead and do that together. So proof. And it's okay if you need to give yourself more space, maybe introduce another piece of paper. You can always put more paper into your workbook. So we're going to write proof. So since the limit as n goes to infinity of our b to the n over a to the n is equal to 3 over 2, which is positive and finite. And the series of a to the n's, which was the sum of 1 over n, is a divergent p series. Since here p is equal to 1. The given series, I'm not going to write out the entire term because we know what I'm referring to, also diverges by the limit comparison test. All right, and there we go. There is our formal proof of our conclusion. So we can walk through, make sure we have all of the correct features here of a formal proof. We're using a complete sentence. We're providing the theorem or test that we're using, so limit comparison. We're stating and providing work for the pieces involved in that theorem, meaning in order to have the conclusion that we make, that our series diverges, we need to provide this other series, the a to the n's. We need to provide the limit of the ratios. We need to know the convergence of that a to the n series, conclude why it converges. So giving all of that background, that justification for every piece of our proof. All right, looks good. Awesome. Thanks so much for watching. So from here, we just have a couple more theorems and one more example. Keep up the hard work.